There is a rule in physics so fundamental, so deeply embedded in every equation we trust, that most scientists never think to question it. It goes like this. You cannot simulate a quantum system accurately unless you have another quantum system of at least equal complexity to run it on. For decades, this rule was the wall. It was the reason physicists accepted that certain structures, certain exotic states of matter, certain arrangements of particles so strange and fragile they can only survive under the most extreme conditions in the universe would remain beyond the reach of human experiment. You could describe them mathematically. You could prove they should exist somewhere in the laws of nature, but you could never actually build them, never hold them, never watch them behave in real time in a laboratory. They belong to the category of things that are real in theory and unreachable in practice. In 2023 and into 2024, researchers at Google Quantum AI quietly crossed that wall. What they simulated was not a molecule, not a simple magnetic system, not the kind of quantum chemistry problem that appears in every quantum computing roadmap slide. What Google's team simulated, using a processor called Sycamore, was something physicists had debated for nearly 50 years, a state of matter so deeply paradoxical that Nobel laureates had built careers arguing about whether it could exist at all. They called it a non-Abelian topological phase. And the disturbing part, the part that has kept certain corners of the physics community unusually quiet since the results were published, isn't that Google simulated it. It is what that simulation revealed about the nature of the particles inside it. The particles behaved as though they had memory, not metaphorical memory, not a loose analogy, a precise, measurable physical memory of every path they had ever taken, encoded directly into the geometry of space itself. Researchers who reviewed the results were careful with their language. Several declined to comment publicly. Others offered qualified statements that, to anyone reading closely, suggested a level of discomfort that peer-reviewed language is not well designed to express. One of the most direct responses came from physicists outside the Google team, who noted that the results, if fully verified and extended, would represent not just a new phase of matter, but a new way of storing information in the universe, one that may be fundamentally indestructible by any process we currently understand. Before we go further, we need to understand what exactly was being simulated and why its existence inside a quantum processor should, by the ordinary rules of physics, have been impossible. The story begins in 1982 when physicist Robert Laughlin published a paper explaining a deeply mysterious experimental observation. When certain materials were cooled to near absolute zero and subjected to powerful magnetic fields, their electrical resistance didn't vary smoothly. It changed in precise, locked steps. Each step corresponded to an exact fraction, 1/3, 2/5, 3/7. These fractions had no obvious explanation. Classical physics offered nothing. Standard quantum mechanics offered nothing. What Laughlin eventually realized, work that would earn him a share of the 1998 Nobel Prize in Physics, was that electrons in these extreme conditions weren't behaving as individual particles at all. They were collectively organizing into something new, a quantum fluid with properties that could only be described by topology, the branch of mathematics that studies shapes and spaces that remain fundamentally unchanged even when stretched, twisted, or deformed. Out of this quantum fluid emerged something stranger still, quasiparticles. Not real particles in the ordinary sense, not electrons, not photons, not anything in the standard model. Quasiparticles are collective excitations of the fluid, ripples in the organized quantum state that behave from the outside like individual particles with their own mass, charge, and spin. And some of them, the ones predicted to emerge in the most exotic topological phases, had a property that seemed almost designed by a science fiction writer. When you moved two of these quasiparticles around each other, the quantum state of the entire system changed permanently. And when you moved them around each other again, in the reverse direction, the quantum state changed again. But not back to what it was before. The two operations didn't cancel. The order in which you performed them mattered, and the system remembered. To understand why this is so deeply strange, consider for a moment the mathematics of ordinary physical operations. When you rotate a book 90 degrees clockwise and then flip it face down, you arrive at a different final orientation than if you flip it first and then rotate. This is non-Abelian behavior in everyday life, and it's why robotics engineers and aerospace navigation systems have to account carefully for the order in which rotations occur. But this non-commutativity, this order dependence, exists at the level of rigid bodies. You can see it, you can undo it, there's nothing mysterious about it. The non-Abelian behavior of anyone's is different in a fundamental way, because it doesn't exist in any single particle. It exists in the quantum state of the entire system. The record isn't kept in any local object you could point to. It is distributed across the whole, encoded in something that topology, the mathematics of shape and continuity, is the only language capable of describing. Topology, to be precise about it, is the branch of mathematics that studies properties preserved under continuous deformation. A coffee mug and a donut are topologically identical because one can be continuously deformed into the other without cutting or tearing. A sphere and a donut are not topologically equivalent because converting one to the other requires a fundamental change in structure. These distinctions aren't about measurement or scale, they are about categorical difference at the deepest level of geometric description. When physicists say that information in a topological phase is protected, they mean something precise. The information is stored in a topological property of the quantum state, a property that survives any continuous local perturbation, because no local perturbation can change a topological category. The only way to corrupt the information is to perform a global operation, one that affects the entire system simultaneously. And that is, in natural thermal environments, extraordinarily unlikely. In mathematics, this is called non-Abelian behavior, named for the Norwegian mathematician Niels Henrik Abel, whose work on group theory revealed that most ordinary operations commute, meaning the order doesn't matter. 2 plus 3 equals 3 plus 2. Rotate a sphere 90 degrees to the right, and then 90 degrees upward, or reverse the order, and you end up in the same place. The universe, at the scales we experience it, is largely abelian. But these quasiparticles, these non-Abelian anyons, are not. They keep a permanent record of every movement they have ever made, written into the topology of their quantum state, and nothing, no amount of vibration, no thermal fluctuation, no ordinary disturbance from the outside world can erase it. Then something unexpected happened. Physicists realized that this bizarre property wasn't just theoretically interesting. It was potentially the most valuable property any particle could have for the purpose of building a quantum computer. The single greatest enemy of quantum computing is decoherence. Qubits store information in quantum states that are so delicate, so sensitive to any interaction with the outside world, that they collapse almost immediately without constant, elaborate error correction. The entire engineering challenge of building a useful quantum computer can be reduced in large part to a single problem: keeping qubits alive long enough to be useful. Conventional approaches to this problem involve surrounding qubits with layers of hardware designed to detect and correct errors before they accumulate. It works, as Willow demonstrated, but it requires enormous overhead. Thousands of physical qubits to maintain a single reliable logical one. Non-Abelian anyons offer a completely different solution. Because their information is stored not in the state of any individual particle, but in the global topology of the entire system, local disturbances cannot reach it. You would have to disturb the global topology itself to corrupt the information, and that requires moving the anyons far apart from each other in a coordinated large-scale way. Random thermal noise, microscopic vibrations, stray electromagnetic fields, none of these can corrupt topologically encoded information because they are too local, too small scale to touch something woven into the geometry of the whole. This is what physicists call topological protection, and it would, if it could be reliably engineered, make quantum computers not just better, but categorically more stable than anything currently on the table. Physicists have known this for decades. The theoretical framework for topological quantum computing was laid out with particular clarity by Alexei Kitaev, a mathematician and physicist who published foundational work on the subject in 2003 while working at Caltech. His framework described how non-Abelian anyons could be braided, moved around each other in controlled sequences to perform quantum computations that would be immune to nearly all sources of error. The idea was elegant, profound, and for 20 years, largely impossible to test experimentally, because non-Abelian anyons had never been unambiguously observed in the real world. This is where the story gets deeply uncomfortable for the physics community, because the history of attempting to observe, create, or confirm non-Abelian anyons in real physical systems has not been a story of steady progress. It has been a story of false starts, retracted papers, and one episode in particular that shook the credibility of a major research institution in ways that still haven't fully healed. In 2018, researchers at a Microsoft-funded laboratory published a paper in Nature claiming strong experimental evidence for a particle called a Majorana fermion, a particle that is its own antiparticle, and that was predicted to behave as a non-Abelian anyon in certain superconducting systems. The results were celebrated, then scrutinized, then re-examined. And in 2021, after an independent review of the underlying data identified critical inconsistencies in how the results had been analyzed, the paper was retracted. Not corrected, retracted. It was one of the most high-profile retractions in experimental physics in recent memory, and it cast a long shadow over the entire field of topological quantum computing. Teams that had been building on those results had to stop and reassess. Funding discussions were affected, and a community already cautious about extraordinary claims became dramatically more cautious about anything involving anyons, Majorana fermions, or topological phases. The retraction revealed something uncomfortable about the field's history. For decades, theorists and experimentalists had been working in a kind of productive tension. Theorists produced increasingly detailed predictions about what non-Abelian topological phases should look like, what signatures they should produce in experimental data, what mathematical invariants should be measurable if they were genuinely present. Experimentalists, working in cryogenic labs around the world in semiconductor systems, superconducting junctions, cold atomic gases, and quantum Hall samples, searched for those signatures and occasionally found hints, tantalizing hints, signatures that looked like they might be what everyone had been searching for until, under the right scrutiny, they dissolved into alternative explanations, a background feature in the noise, an artifact of a particular measurement technique, a real phenomenon, but not the one claimed. The history of non-Abelian anyones before 2023 is in large part a history of near misses and careful disappointments, punctuated by genuine theoretical progress and the occasional retraction. This is the landscape Google's team was walking into when they designed their experiment. And this is where things get disturbing in a precise technical sense, because what Google did was not attempt to observe non-Abelian anyones in a natural material. They didn't cool down a semiconductor or engineer a superconducting heterostructure and hope the right exotic physics would emerge. They did something more direct, and in some ways more audacious. They used a quantum processor to actively simulate the mathematical conditions under which non-Abelian anyones should exist, and then they watched what emerged. The approach required a carefully designed sequence of quantum gates, operations applied to the qubits of the Sycamore processor in a specific order, meant to engineer a quantum state whose mathematical properties match those of a non-Abelian topological phase. The team, working under the leadership of Google's Quantum Research Division and collaborating with external physicists, then performed operations on the simulated system analogous to braiding, moving the simulated quasiparticles around each other in the carefully orchestrated paths that non-Abelian behavior would predict. If the system was behaving correctly, as a genuine non-Abelian topological phase, the braiding operations should change the quantum state in specific, measurable, non-commuting ways. The result of braiding A around B should differ from the result of braiding B around A, not by a small amount, definitively, measurably, in a way that standard quantum states simply do not behave. To appreciate the difficulty of what this required, consider the scale of the engineering problem. The Sycamore processor operates at roughly 10 millikelvin. The gate operations needed to prepare the topological state, and perform the braiding had to be executed with timing precision measured in nanoseconds. Even the smallest deviation from the intended sequence, a single gate applied slightly out of order, a small calibration error in any individual qubit's interaction parameters, could destroy the delicate topological state before the braiding was complete, and leave the researchers with noise rather than signal. The team had to design and validate the entire gate sequence, then run the experiment enough times to build up statistically meaningful data, distinguishing the genuine non-Abelian signature from the background of ordinary quantum noise. The verification approach involved carefully chosen topological invariants, mathematical quantities that should have specific values if non-Abelian order is genuinely present, and measuring them directly from the processor's output. The results, published in 2023 in the journal Nature, showed exactly this. The braiding operations produced distinguishable quantum states. The non-Abelian behavior appeared cleanly, reproducibly. What came next changed the conversation in ways the physics community is still processing, because the question immediately arose, and it was not a rhetorical one. What had actually been created? Google's team was careful. Their paper described the result as the first observation of non-Abelian topological order and anionic braiding in a quantum processor. They used the word observation, not simulation, not recreation. Observation. From a strict reading of the experimental data, this distinction is defensible. The quantum processor was not running a classical simulation of a topological phase, a conventional computer solving equations to approximate what one might look like. The qubits were physically prepared in a quantum state with genuine non-Abelian topological order. The braiding was performed on that state. The resulting measurement was a direct physical measurement of a quantum system that was, within the processor, exhibiting the behavior. Whether you call that a simulation or a creation is not a trivial semantic question. It depends on a deeper question. What is the difference between faithfully physically realizing a quantum state and observing a naturally occurring one? Some physicists argue there is no meaningful difference. A state with genuine topological properties is a state with genuine topological properties, regardless of how it was prepared. Others argue that what Google built is an analog quantum simulation, an engineered environment designed to mimic the mathematics of a topological phase without necessarily producing everything a naturally occurring physical example would. The debate is live, active, and unresolved, which is precisely why so many researchers have been measured in their public responses. But the real mystery had only just begun. Because underneath the technical debate about nomenclature and methodology, a stranger implication was building quietly. If non-Abelian anyones can be reliably created and braided inside a quantum processor, and if the information encoded in their braiding is genuinely topologically protected, then what exists inside that processor, for the duration of the experiment, is a physical system with a property that has no counterpart anywhere in the ordinary world we experience. Consider what topological protection actually means in physical terms. Every piece of information you have ever stored, on any medium, in any form, is fragile against the right attack. Hard drives fail, neurons misfire, books burn. Even the most durable physical encoding eventually succumbs to entropy, to the slow, relentless, disordering tendency that governs every process in the observable universe. But topologically encoded information resists this, not because it is armored or redundant in the conventional sense, but because the information exists in the geometry of a quantum state, in a global property of the whole system that local disturbances simply cannot reach. It is, in a real physical sense, protected by the shape of the thing itself. There is something quietly extraordinary about that idea, and it becomes stranger the longer you sit with it. The universe, at the scale of everyday experience, constantly erases. Heat, death, entropy, the arrow of time. Everything we know about thermodynamics suggests that information, left alone, degrades. Yet embedded within the laws of quantum mechanics, in the topology of certain exotic states, there appears to be a mechanism that resists this. A way of encoding information not in any particular particle or position, but in a mathematical relationship so fundamental that the ordinary processes of physical decay cannot find a handle on it. There is a useful way to think about what topological protection is doing, physically. Imagine you wrote a message, not on a piece of paper, but into the structure of a knot. Not the position of the string, not the color of the fiber, but the topology of the knot itself, the number and arrangement of crossings in a way that is preserved no matter how you stretch or twist the string, as long as you don't cut it. A local disturbance, a tug here, a push there, cannot change which topological knot type you have. It might change the shape, but not the category. The information encoded in the category survives. Non-Abelian topological order does something mathematically analogous in a quantum state. The information is encoded not in any local degree of freedom, but in a global topological property, a property that only changes under operations so drastic and coordinated that ordinary thermal noise, ordinary decoherence, ordinary environmental disturbance simply cannot produce them. This is, to be precise, not perfect protection. Topological protection has limits. If the energy gap that separates the topological phase from other states is too small, thermal fluctuations can eventually bridge it. At sufficiently high temperatures, or with sufficiently strong local perturbations, even topological order can be disrupted. The protection is relative, not absolute, but relative to what any other encoding approach can offer at the quantum level, it represents a qualitative leap in durability, one that theoretical physicists have considered the most promising long-term path toward genuinely fault-tolerant quantum computation since Kitaev's foundational work 2 decades ago. Researchers across several fields are asking, though mostly in private, whether this tells us something about information itself that we haven't yet properly incorporated into our picture of physics. Stephen Hawking's long battle with the black hole information paradox, the question of whether information that falls into a black hole is truly destroyed or merely hidden, was one of the most consequential debates in physics of the last 50 years. The insight from topological quantum matter that some forms of information encoding are inherently more durable than others does not resolve the Hawking paradox directly. But it complicates the assumption that information and entropy always move in the same direction. It suggests that nature, under the right conditions, knows how to protect information from its own tendency toward disorder. Researchers who have spent their careers studying quantum information theory have noted this quietly in papers and conference presentations that don't make mainstream science headlines. The connection between topological protection and the deeper question of information's role in the structure of reality has not yet crystallized into a major research program. But the people who study this most closely are watching what Google's team has opened very carefully. Here's where the story arrives at its final, most unsettling layer. If the non-Abelian topological phase demonstrated by Google represents a state of matter or a state of quantum information that is genuinely topologically protected, that cannot be corrupted by local noise, then what was held inside the Sycamore processor during that experiment was, by definition, more stable than anything that exists in the naturally occurring world around us. More stable than diamond, more stable than the bedrock of mountains. More stable, in a specific but technically precise sense, than ordinary matter itself. Not because it was harder or denser or chemically inert, but because its defining properties existed at a level of physical reality that ordinary physical processes cannot reach. And it was built, not found. Engineered, not excavated. Created inside a chip the size of a matchbook. Cooled to temperatures colder than deep space by a team of physicists who, by all accounts, were not entirely certain beforehand that it would work. The silence from parts of the physics community in the aftermath of the Nature publication is, depending on how you read it, either appropriate scientific caution or something more telling. Researchers who study topological phases of matter do not have a strong institutional incentive to be publicly enthusiastic about results produced by an industrial research lab using an approach different from their own. The history of the field, shadowed by the Microsoft retraction and by decades of theoretical predictions that proved experimentally elusive, has made everyone careful. But caution in tone is not the same as disagreement in substance. And several physicists who have examined the paper have stated, with varying degrees of directness, that the results appear to be real, that the methodology is sound, and that what Google's team produced constitutes a genuine experimental advance in a field that desperately needed one. What remains is the question of what comes next. Google's roadmap toward fault-tolerant quantum computing has long included topological qubits as a potential endgame, a way of building logical qubits that are protected by geometry rather than maintained by exhausting layers of active error correction. The experiment published in 2023 was a proof of concept, not a working topological qubit. Moving from demonstrating non-Abelian braiding in an engineered quantum system to reliably using that braiding to perform arbitrary quantum computations is still a significant research and engineering challenge. Microsoft has been pursuing topological qubits through a different physical approach, using semiconductor nanowires rather than a programmable quantum processor, and despite the 2021 retraction, has continued to publish research in this direction. The race toward topological quantum computing is real, active, and involves some of the best resourced research teams in the world. But somewhere beyond the roadmaps and the funding announcements and the carefully worded press releases, the deeper question persists. What Google's team created inside that processor, even briefly, even in a form that required extraordinary engineering to maintain, was a physical system exhibiting behavior that has no parallel in the familiar world. Particles with memory written into the geometry of space, information encoded in a form that ordinary physical reality cannot corrupt. A state of matter that, until 2023, had never been observed behaving this way under controlled conditions anywhere. Physics has occasionally produced results like this before. Results that are technically impressive, carefully measured, fully peer-reviewed, and yet somehow feel like they are pointing at something larger, something about the deep structure of reality that the immediate paper cannot fully contain. The experimental confirmation of entanglement was like that. The first detection of gravitational waves was like that. These results were celebrated, and then, slowly, their implications rippled outward into fields their original researchers hadn't anticipated, changing the way entire disciplines thought about fundamental questions. It is too early to say with confidence that what Google's quantum team created belongs in that category. The researchers themselves have not claimed it does. The paper is careful. The language is technical. The conclusions are bounded. But there's a reason the results produced silence in some corners alongside celebration in others. There's a reason physicists who study the deepest foundations of quantum mechanics are watching this line of research with unusual attention. Because what was simulated inside that processor, a state of matter that braids memory into the geometry of space, that stores information in a form beyond the reach of ordinary physical decay, that demonstrates a non-commuting, path-dependent behavior, that the everyday world simply does not exhibit, belongs to a category of physical phenomena that our intuitions were never built to handle. The implications extend further than most public discussions have yet acknowledged. Theoretical physicists working at the intersection of quantum gravity and quantum information have long suspected that the geometry of space-time itself might be, in some deep sense, emergent from quantum entanglement. Juan Maldacina's ADS CFT correspondence, one of the most studied theoretical frameworks in modern high-energy physics, describes a precise mathematical relationship between gravity in a higher dimensional space and a quantum field theory living on its boundary. In this framework, the connectivity of space, the very fabric of space-time geometry, is tied directly to the entanglement structure of the quantum theory on the boundary. Areas of space-time that are strongly connected correspond to strongly entangled regions in the quantum description. Space-time itself, in this picture, is not fundamental. It is woven from quantum information. If this picture is even approximately correct, then a state of matter that stores information in the topology of space, that uses the geometry of connections as its memory medium, is not just technologically interesting. It is a small, engineered echo of the mechanism by which the universe itself might be organizing its information at the deepest level. Google's Sycamore processor, cooled below the temperature of interstellar space, briefly contained a system that arranged its information the way some of our best theories suggest the geometry of space-time arranges its own, not as a metaphor. has a physical, measurable quantum state. That claim is speculative in the sense that the connection between the AD-CFT framework and the specific topological phase created in the Google experiment has not been formally established. Physicists would correctly object to drawing that line too boldly. But the fact that it can be drawn at all, even tentatively, even as a question rather than a conclusion, tells you something about the territory these results have entered. We live in a universe where everything eventually wears away, where entropy always wins, where information, left to its own devices, dissolves, and inside a chip cooled to the edge of absolute zero, a team of researchers built for a brief but measurable moment, something that quietly defied that rule. The universe, apparently, has been hiding more than we knew. It has been hiding states of matter so exotic that 50 years of theory were required even to describe them, and another 20 years to begin finding the tools to build them. It has been hiding properties of information so counterintuitive that the entire experimental tradition of physics had to wait for the right machine, running at the right temperature, operated by the right team, to touch them for the first time. And somewhere in the deep chill of that Santa Barbara laboratory, inside a chip running operations timed to the nanosecond, the boundary between what exists and what merely ought to exist, the boundary that is held for every physicist who ever worked in this field, quietly, measurably, moved, we have only just built the instrument sensitive enough to find it. And we do not yet fully understand what we found.